Hey everybody, welcome to our introduction to confirmatory factor analysis. I want to start off just kind of talking about the reading sum. I do want to say if you haven't already done some of the readings, then I would stop the video right before we get to the R walkthrough because I'm going to use some terminology that may not be familiar if you haven't done the readings. But just to give you an idea of what's in the readings, we'll kind of talk through them a little bit right now. Probably a good place to start is this Newsom article where he talks about the concept of a latent variable. What is a latent variable? And he kind of explains it in in a way we've been talking about how we think of any observed score is really made up of the true score plus some random error. And it relates that to how a latent variable is to, we can think of the latent variable like a true score that isn't directly observed. And the observed measure that we do see is a manifestation of that true score plus some random error. So I thought that it's a really good idea to get your head thinking about what is a latent variable. He also has a really good section on the effects of measurement error. I don't know if you remember from the first assignment, there was a question on there about how the unreliability of a score, how it can affect other statistical tests, and he has a good walkthrough here about that. About how measurement error can affect like regression coefficients, correlation coefficients. So you can kind of read through this and see. He also talks a little bit about here, the ideas about how factor loadings are actually derived in a interesting way to kind of think about it. So it's a good way to start wrapping your head around some of these concepts that we're going to be talking about. Another good, really short, it's only a couple pages, introductory article is this one, the confirmatory factor analysis and communication research. It's a good place. It's a really short intro to really get your get your feet wet on some of these topics. The Santor chapter I thought was another good general overview of confirmatory factor analysis. It's pretty easy to follow, and they walk through an example here. So I would definitely probably recommend this chapter, and it's pretty short too. This Klein chapter is very in-depth. It goes through both exploratory and confirmatory factor analysis. So a lot of the stuff that we've already talked about in EFA, he talks about in here too. But he also covers a lot of new stuff in confirmatory factor analysis. And Klein is one of the renowned experts on confirmatory factor analysis and structural equation modeling. He has one of the best books on structural equation modeling too. So, and he presents it in a very easy to understand way too. I missed the CFA part. I was just going to show you so he goes through an example. He talks about, all the different things about parameter estimation, fit indices, modification indices, what do we mean by, the model needs to be identified. He walks through kind of all of those things. So, and that's another great place to start. Another good introduction article is from Hotz. I believe it's in the optional readings because it really focuses on structural equation modeling. But the first part of it, the first step in a structural equation model is what they call establishing a measurement model, which is essentially a confirmatory factor analysis. So he has a good introduction here too. You'll notice in a lot of the readings, a lot of time, a lot of the stuff, information will repeat itself. I kind of err on the side of providing you too much information. I'd rather provide you more than not enough. I'd rather, if I give you one article that summarizes CFA and you don't really understand it, I want to have a second one that you can also review. So that's kind of my thinking behind giving you a lot of these readings. If you start reading this, you're like, oh, I really kind of already understand what's going on. Skip it and go to the next one. Then I have several articles on here. This Jackson article, this McDonald article that talk about reporting practices. How do you interpret the CFI, the root mean square error approximation? Like, what are good values? How do we go about reporting results of a confirmatory factor analysis? And that's what these next few articles do. This Jackson article, this McDonald and Ho article, the Schreiber article. These are all, just general overviews of how we would report our results from a structural equation model or a confirmatory factor analysis, rather. And then how do we interpret some of the different fit indices that these programs report. Here's another just considerations in confirmatory factor analysis. This is a good article. It's pretty long about how CFA and EFA fit into the scale development process. What is their role in helping establish the validity of our survey. So it's a really good article on here too about it. This Afrin article is really a walkthrough of using the Laven package that we'll be doing. So it's kind of going to be similar to the one that I'm going to walk you through too, but here's another one too, where he shows you the R code, to read your data, and how you fit your model and Laven, and then kind of some interpretation guidelines. And that's what I'm going to go through in this video too. FIRE has a great introductory chapter, a good overview of confirmatory factor analysis. If you don't have the book, here is a chapter. It's from an older edition of the book. But if you have the book, it's the same chapter. I think this was the edition before this new one. But that's on there too, and it's a really good overview introduction into confirmatory factor analysis. Here's our SPSS anxiety questionnaire. I'm going to save this because we're going to use these same data in the confirmatory factor analysis, and we might refer back to this document in a minute. So the CFA script should already be on Canvas for you, and I've annotated the script file very heavily. You'll see in here. So the basic idea of a CFA is we want to test whether whether some theoretical model that we've developed, whether our data are a good approximation, rather, of that model. And so in exploratory factor analysis, we didn't have any theory or anything really guiding how we, what factors were going to emerge. And it was really more exploratory, right? We were interested in, what are the underlying factors from our SPSS anxiety questionnaire, so to speak. In confirmatory factor analysis, it's really theory driven, right? So we already have a theory in place, and we want to test whether or not that theory is valid or not, right? So this SPS anxiety questionnaire was supposed to measure 4 constructs. was it statistics sphere, computer sphere, math sphere, and peer evaluations were the 4 factors that we said we're supposed to evaluate. So now let's take the data and see if the data fit the theory that we have. The main package we're going to use in R is this LAVEN package. It stands for Latent Variable Analysis, LA, Latent Variable Analysis. We're also going to use the LAVEN plot command, and then we'll use our friendly psych package again, and then there's some SEM tools and a package for multivariate normality that we'll also install here as well. So let's get our packages loaded, and then we're going to load our data set. Remember, before we when we ran our EFA, before we did it, we decided to randomly split the data in half, and we were going to run the EFA on one half of the data and the CFA on the other. So we're not just confirming, we're not confirming our data on the same data that we developed our theory on. So we're going to load the data, the half we didn't use for the EFA, and run our CFA on these to just make things a little bit easier. Remember how the data were named? Remember in that file, the variable names were question_01, question_02. Well, since we're going to have to refer to these variable names, I'm just going to change them just to make them a little bit easier to manipulate, and rename them just Q1, Q2, Q3, so I don't have to write out the word question 1, 2, 3. So that's just going to make things a little bit easier. Before we run our CFA, we can just check some preliminary statistics. We can check our data set for missing data. Make sure the minimum and maximum values are reasonable. We want to check that all the response options were used. There's a few functions in the psych package, that we can do these, so we can look here, use the describe function in psych, and, it just basically gives us descriptive statistics. For our data, we can get the mean, the standard deviation, the median, the min and max, the skewness and kurtosis of our data. We can get basically, frequency distributions, basically the proportion that answered each response option and the number missing. If you remember, these data didn't have any missing data, so it really wasn't much to worry about. And then all the response options seem to be used. You look at question 2, doesn't look like very many people or no one selected strongly agree, I believe, for it. And we can look back here. My friends will think I'm stupid for not being able to cope with SPSS, so you can always refer back. Anyways, we want to see whether these data confirm basically what we found in the EFA. So here in the script file, I basically just copied the subsetting syntax we have, so we can remember, peer eval was made from questions 2, 9, 19, 22, 23. The stat peer items were question 1, 3, 4, 5, 16, 20, 21. So that was basically just to give up, just so I can remember, we can write our CFA syntax. There was a couple things, just notes to remember from our EFA. Q12 had some strong cross loadings. Question 3, 16, 4, and 5 also had some strong cross loadings. We're just going to ignore those right now and go with the factor that they loaded most highly on. Remember, Perryville also had a really low reliability. We're just going to ignore that for right now and keep it in our CFA. We can say we have some strong theoretical justification for it. So the first thing to do when you're setting up your model is you need to tell the program, well, what model, what is this theoretical model that you want to test. And in Laven, that means, defining your model. Here's some symbols to get you used to what's going on in Laven. We use an equal and a little tilde sign here. That means that, our latent variable is measured by or being defined by these observed or manifested variables. You just use the little tilde symbol for, say, like, y is regressed on x. You would use two tildes to establish a correlation or a covariance between two variables, and you'd use little tilde and a 1 to represent an intercept. On Canvas, there's a link to the Laven website. It's very well documented, and I would highly recommend looking through it. It's got some great tutorials to go through, and it talks about these different things, but I'm trying to cover it, in here as well. So, remember, the main goal in CFA is really to try to explain the relationships among the observed variables by specifying some hypothetical relationship between them. So the first thing we want to do is, tell the program what model it is that we want to estimate. So here I've named our model SAQ model, so the SPSS Anxiety Questionnaire model. And this first line here, so in the Laven syntax, we put this all in quotes. Notice it starts with a quote and ends with a single quote. And I'm going to say, computer fear is measured by question 6, question 7, plus question 10, 12, 13, 14, 15, 18. Remember, that's the same thing we found in the EFA. That's how I'm defining these. I'll say our stats fear is measured by question 1, 3, 4, 5, 16, 20, 21, and so on. So you kind of get how we define these. One reason that the Laven syntax is very succinct compared to other structural equation modeling programs is Laven makes several defaults for their model. So in confirmatory factor analysis, Laven will fix the factor loading of the first indicator of the latent variable. So here, the factor loading for question 6, question 1, question 8, and 12 will all be fixed to 1. It'll set the loading to 1. It'll also, by default, add residual covariant, or add covariances between the latent constructs by default. So this would be analogous to doing an oblique rotation in EFA where your factors are correlated. It automatically correlates all of your factors. So you might ask yourself, why does Laven fix the loading of the first factor to 1? The main reason is, latent factors aren't measured, so they don't have any kind of scale. In order to come up with a solution, the estimator needs to scale the latent factors somehow. So one way to scale the factors is to set the loading of the first factor to 1. That's its default behavior. Another option is we can constrain the latent factor. Basically, we can standardize the latent factor. We can say the latent factor has a mean of 0 and a variance of 1. either one of those approaches gives you equivalent results. It's basically the difference between them, if you think about it in like regression terms, is you get unstandardized results, like unstandardized regression coefficients, and standardized regression coefficients. Some people like the standardized, like standardizing the latent variables. So then, covariances between the latent factors you can interpret as would be correlations. And then the factor loadings are interpreted similar as factor loadings in EFA. Remember the EFA analyzes a correlation matrix, so the factor loadings are standardized. And, you typically, factor loading is greater than, 0.5 to, 0.7 or, would be considered strong. Those would be analogous to the standardized factor loadings in CFA. So we're going to go with this default behavior, and I'll show you how you can change it in a minute. So, once we've set up our model, we have our model set up here. All we have to do is run the CFA function to fit our model. I'm going to call this just our first model fit. So basically the command, function is CFA. You give it your model, and then what data you want to fit it to. The SQ CFA. Oh, whoops, I never ran I was talking too much and never ran our model syntax. There we go. Now, let's fit our model. Okay, it's fit. And then let's just get a summary of our model. Here we go. So the first thing you can see is that it gives you the Laban version number. It ended normally after 58 iterations. It tells you the number of free parameters here. I'll show you later on how that's calculated. The number of observations in the data set, you can check to make sure that's correct. It gives you some an overall fit indice. We'll talk about fit indices a little bit later. It gives you here your factor loadings. Remember the factor loading for the first indicator for each latent factor was fixed to 1. This is, they call it the marker method. So you can see that happen. Notice you have some factor loadings greater than 1. In EFA, would be like, whoa, what's going on? Factor loadings can't be greater than 1. That indicates there's a problem. We call them Haywood cases. Remember, these are unstandardized factor loadings, so don't freak out right now that they're greater than 1. They're not standardized yet. Remember, question 3 loaded negatively on the stat fear items. That was that standard deviations excite me. You can still see that is going on. So you get all your factor loadings here. You get your covariances between your factors. Now these are actual covariances. They're not correlations. If we standardize them, they would be correlations. And then here are your error variances here for your indicator variables. If you want to get a graphic, a plot of your model, you can use this Laban plot function package here. There's also a package called SEM plots I'm going to show you later that's a lot more flexible, but this one's, and the syntax for Laban plots really easy to get. You can see, so you can notice that, by convention, we usually use ovals or circles to represent latent constructs and rectangles or squares to represent observed variables. So you can see, when the arrow is pointing from the latent construct to the observed variable to show that, the observed variables are being manifested by this latent construct. We can also add we can add some options, and we can get, here we go. So we get the factor loadings, whether or not they were statistically significant. There's the covariance parameters between them. So you can see, you can play around with the Laban plot to kind of get the figure exactly how you want it. Remember when we talked about there were two different ways to, I guess, conceptualize the structural equation model. There was the marker method and then the standardized method. To get the standardized solution, you can just add to the summary command standardized equals true, and it's going to print both the unstandardized and standardized factor loadings. So you can see here, all the top information is all the same. You have your unstandardized factor loadings here. This STD-LV is where we standardized the latent construct, and the indicator variables are unstandardized. This is what would happen if when we set the error variance for the latent construct to 1. If we go down here to notice that the variance estimates for the latent constructs here, remember they're set to 1. Remember we marked them instead of the first factor loading in this column. The STD all would be analogous to if we standardized all of our indicator variables, questions 6, 7, 8, 10, and we standardized our latent variables, right? We set them to a mean of 0 and a standard deviation of 1. So these factor loadings in these two columns here, you can interpret similar to factor loadings in EFAs. Now, if one of these factor loadings were greater than 1, we'd say, whoa, what's going on? That's indicating that there's what they call a Haywood case. There's a problem in the analysis. So maybe we'd interpret these in a similar manner. We're typically looking for, factor loadings greater than 0.5, greater than 0.7s, probably even better. It looks like here question 10 has a weak factor loading. Looks like everything in the math view constructs loading, pretty nicely. Question 23 here has a pretty low loading. Now you see here where the covariance between factors, and this is correlation then between your factors. So you can see the comp and stat here are pretty strongly correlated, right? 0.83 indicates a pretty strong correlation. There's another pretty strong correlation between computer fear and math fear, was at 0.64. And then a negative correlation between computer fear and peer evaluation. So that's how you can interpret them as correlations. That's why some people like that method better. Different programs, I think Lizral defaults to this behavior. I think Amos and M+ default to the marker method. Don't quote me on that. That's just me trying to remember it from memory. So if you want, here I have some syntax here. If you want to ask for the standardized solution in Laban terminology, this is how you would set up your model. We would take out the first indicator for each of our latent variables and multiply it by NA. That indicates that we want Laban to free that parameter, estimate it. And then we could set then here, remember we use 2 tildes to represent a covariance, and we want to set the covariance for each one of the for each one of the latent variables to 1. If we do that and we run it, notice that this solution is the same thing as in that STD-LV, standardized latent variable solution. 0.65, 0.762. Here we go, 0.65, 0.762. So you still get the same results either way. To me, it's just easier to add in standardized equals true, and you can get both of them. Here we make sure the variance estimates are all set to 1. You can see these correlations are the same as we found in the other solution. So standardized solutions aren't the only options we can request from the summary function. We can get the standardized solution. We can get additional fit indices, and we can also request R-squared values or communalities. Remember what those were from EFA. Now our output's a lot longer here. So fit measures equals true prints numerous different fit indices. There are several handouts on Canvas. There's even a good website to David Kinney's site where he talks about pretty much each one of these fit indices and gives you general recommendations for how to interpret them. We look through here, and the fit indices for this model aren't great. The model chi-square test here is testing whether the observed it's testing whether the model implied covariance matrix is a good representation of the observed covariance matrix. We really want this to be non-significant, because then that would tell us that the model implied covariance matrix is not different than the observed covariance matrix, and that's what we want. I would say that our model is a good representation of these data. In practice, this chi-square test is very sensitive to sample size, so it's not unusual for this chi-square statistic to be statistically significant. So that's why a lot of these other fit indices have been developed. There's another rule of thumb where you can really divide the chi-square statistic by its degrees of freedom. If that's less than 3, then it's generally a good fit. If it's less than 2, it implies there's great fit. Ours equals about 6. So, we're saying it's not great fit. This model test baseline test test whether this model is better than the worst possible model, which would be one of the readings calls it a null model, in which the relationship among all the observed variables, there's no relationship among all of the observed variables, and yeah, it's a good thing this one is statistically significant. There are some other just overall fit statistics like the CFA and the TLI, Tucker-Lewis Index, the Comparative Fit Index. Typically, we want these to be greater than 0.9, greater than 0.95 is even better. A 1 indicates perfect fit. We're at 0.88 and 0.86, so it's not all that great. The AIC and BIC, these are really used to compare different models. We can compare nested and non-nested models with both the AIC and the BIC. The root mean square error of approximation, remember we calculated that in the EFA video too. We typically want it to be less than 5. We're right about 0.6. And then we have a p-test testing whether the root mean square of approximation is less than or equal to 0.05. So we want this test again to be not statistically significant. This is also known, sometimes you'll see this called like the p-close or the p of close fit value. Typically, root mean square, you'll see less than 0.8 is okay. Less than 0.05 is better. So, we can say our fit here is okay, but it's not great. You also don't want the confidence interval to contain 0.1, so that's a good thing. And then we have the standardized root mean square residual, the SRMR. And we typically want it to be less than 0.8, less than 0.06, sorry, 0.08. Less than 0.06 is even better. So we're okay here. A lot of the readings give lots of different recommendations for these. So I'll let you kind of look through that and see. And a lot of times they don't always agree about what is a good fit. So they're generally around the same range, but people will give slightly different cutoff values. Just because your model, just as the model fit says the model fits a good model, doesn't mean it's necessarily quote unquote a good model, or it reflects the reality in any way. Really in confirmatory factor analysis, the theory behind your model is really crucial to deciding whether your model is good fit or not. I mean, you could really play around with CFA and, changing up your model, and, you can get your model to have really great fit, but it might have, nonsensical relationships between your variables. It might not make theoretical sense. So really, you really have to have a solid theory in place before to use this type of procedure. If you don't, then confirmatory factor analysis really isn't the right tool for you. So if we come on down here, we get the same. There's our factor loadings. There's the correlations or covariances between variables. Here's our residual variance estimates again. And here's our R squares or our communalities. Remember the communalities indicate the proportion of variance in our indicator that's explained by the latent variable. So we want, remember, we think of the variance in the variable with this common variance that's shared between it and the factor, and then unique variance that's unique just to that variable, and then that unique variance can be separated into error variance as well. So remember, the communalities represent the proportion of variance in the indicator that's explained by the latent variable, and generally we want to see that that the latent variable is playing a good deal of variance in our indicators here. Some rules of thumb I've seen before is, you want these to be greater than 0.5. If they're greater than 0.5 indicates we should keep that indicator. Usually if it's less than 0.3, we might want to say, hey, what's going on? Look at like question 23 here. Only about 6% of the variance in that indicator is being explained by the latent construct. So maybe it's not, maybe that indicator isn't doing a good job. Sorry, I got that backwards. Maybe that latent variable isn't what's really manifesting this observed variable. We go back, remember it had a pretty weak factor loading there too. So we'll talk, maybe that's something we want to keep an eye on here. So in the notes here, like I said, I really tried to annotate this script file a lot so you can kind of read through it as you're working through the syntax. But, just some general things, want to be on the lookout for is, we want our factor loadings to be large. So, around 0.5, 0.6 is what we're generally on the lookout for. R square values, greater than, say, 0.4, this would indicate that the item fits pretty well. The factor fit, people usually talk about the average variance explained by that factor. So that's which is basically, we could look at, math fears being manifested by question 8, 11, and 17. We could come down to these R-square values. Was it 8, 11, and 17? Average those, and we'd get the average variance explained by that latent construct. And you'll typically see average variance explained. You want it to be greater than 50%, so 0.5. You could also they also say that's a good indication of convergent validity. Right, that these factors all explain that factors explains a lot of the variation in those indicators. You can also see this used as an indication of discriminant validity, as well, that this variation is different than the variation being explained by the other factors, right? That, this construct is unique and it's different than these other factors. That's what we're talking about here. You can compare the square root of the average variance explained against the correlation with that factor and the other factors. If it's greater than that, you might say that represents some type of discriminant validity. If you don't want to average these things by hand, the SEM tools has a function in it, a reliability function, and here's your average variance explained, the AVE here. It also gives you, the alpha reliability for each one of the factors and an overall. So you can see the math has a pretty decent average variance explained. So, we noticed our first model didn't fit. The data didn't have great fit. One thing we can do to see, okay, well, what modification can I make that might improve the model fit? Most SEM programs have what are called modification indices. And it basically tells you, if you make this change, it'll make this improvement. And the chi-square will be reduced by this amount, which in turn would indicate better model fit. So, you can really get carried away here with the modification indices, right? So what you have to also think about, statistically, this may make the model fit better, but is that really supported by the theory? You have to keep that in mind when making modifications. So, to run modification indices, the command is just modification indices. You give it the model that you fit. We call it fit one. And now I'm telling it I only want modifications that would reduce the chi-square by 10 units or more. And I want you to sort them with the highest recommendation first. You can change this minimum cutoff value. I use 10 because you're going to see there's a lot if we didn't use that minimum cutoff. And so you can see even with that large of a cutoff, there's quite a few modifications that are suggested. You can see that in the OP column here, this is what, it's using that Levin symbol terminology to tell you what's going on. Remember 2 tildes refer to a covariance. So it's saying if we added a covariance between question 20 and question 21, would reduce the chi-square value by around 119 points. This would be the estimated covariance between them. And I think this would be the estimated correlation. I think this is the standardized value. We can check that in a minute and see. You can see the next modification it suggests, remember, it's an equal and a tilde. So it's saying that we should add question 6. Question 6, statistics sphere should be also defined by question 6. So we have to think, what does that make theoretical sense? Also, if we look at, it's also saying that there would be a negative relationship. So we could also go back to our question set and look. It says, I have little experience with computers. Does that make sense? As stat fear being manifested by that, and should it be negative? Should it be a negative relationship? That's something that you would want to consider. I think I said in here. Yeah, so each of the columns, S, E, P, C, L, V, it would be the factor loading when you standardize on the latent variable, standardizing both variables. So that's how. So it does talk in here about how you can interpret it. Let's look at question 20 and 21. It suggested a covariance between them. I can't sleep for the thought of eigenvectors. I wake up under my duvet thinking that I'm trapped under a normal distribution. Both of these items, have to sort of deal with sleeping in a way. Maybe there is some residual covariance between them. Maybe they're more tightly related than we thought, are more interrelated with each other than with the other items in the stat fear set. So to me, that one makes a little more theoretical sense as to why they would fit better. If we were going to add question 6 as a manifestation of stat fear, we would want to have some theoretical justification for it. Now, the first thing that comes to my mind is, well, why didn't we have that originally? So I would really be hesitant about making this modification change. Generally, what I do is usually make one modification at a time, see how that improves the model fit, the different relationships, and then work from there instead of making multiple modifications to my model at a time. Here's some additional syntax. You can request only modifications to the latent variable structure. You can only request only modifications for covariances here. So those are some syntax there to kind of show you how to do that. So since the largest modification was suggesting letting question 20 and question 21 covary, we're going to try that suggestion first. So here, this would be the syntax to make that change. Basically, the syntax stays the same. Computer fear is being defined by question Q6, 7, blah, 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 all the way down. And then all we're doing is at the end, I'm adding Q20 two tildes to represent a covariance between Q20 and Q21. It's that easy. And see, I added a comment. This specifies a covariance between those. Okay, so let's run that. So we've defined our model. And now let's fit the data using the CFA function. So remember, the function is just CFA, our SAQ model 2, and then the data set. And I'm calling this one fit 2. All right, we fit it. And now let's get the output here. So here I'm going to ask the sum. I want a summary of our second fit of our second SAQ model. I want the additional fin indices. I want the standardized solutions, and I want the communalities there, right? The portion of variance explained. And there it is. Notice our chi-square statistic was reduced from what it was previously, reduced by like, what was it, around 119 points or so. Notice it's still statistically significant, so it indicates it's not the best fit. Notice the CFI slightly increased, the TLI slightly increased. We can compare our AIC and BIC to what the previous model was, and we'll look at that in a minute. A root mean square error of approximation decreased slightly, and the SRMR also decreased slightly. So all these indicate that we had, slightly better fit with this model. Since this model is nested within our previous model, there are fewer parameters here. Sorry, our previous model is nested within this one. Our previous model has fewer parameter estimates than this model. We can do a likelihood ratio test to compare the model fit between them. So you can use, you'll see a lot of documentation online using the ANOVA command. As I was writing this, it looks like Laban had an update and they have this new LAV test, likelihood ratio test. They both do the same thing. The LAV test, LRT, has a few additional options in there that you can use. But notice they give you the exact same result. So whichever one you want to use, you can, look up the help function on the, you can see it pulled up in the viewer here. Notice this one has different options you can choose that the ANOVA function doesn't. But generally, we're really looking at, we get a chi-square difference test. Since the model is nested within each other, we can compare them. We can compare the log likelihoods between the models with the chi-square test, and so the model with the lower likelihood fits the data better. So you can see model 2, where we added the covariance, fits the data significantly better than the model without it. You can also notice that too, the AIC and BICs are both lower for fit 2 than for fit 1. I've also got some syntax here where we can, here we only look at the likelihood statistics. The AIC and BIC are also based on the log likelihood. We can compare some fit indices between them. So that's what I did here. I saved some of the fit measures. We can use the fit measures function, fit measures from fit 1, and I want to grab the root mean square error of approximation, the TLI, the CFI, the AIC, the BIC. And I'm doing the same thing for fit 2 here. And then this is just saying here, I want to bind them together and round to 3 decimal places, so it makes it easier to see. So here for fit 1, it was with no covariation. In fit 2, there was a covariation between question 20 and 21. We can run this syntax, and we can see the model with the covariation had a smaller root mean square of approximation. The TLI was increased, the CFI was increased, the AIC and the BIC both decreased. So it all indicates that our second model fit the data better. So it fit the data better, but it still wasn't great fit, right? So, the fit was improved, but it's still not excellent. We can look at then some different modification indices that are now suggested. from our model. We still get the largest here is between, having stat be also manifested by question 6. We also have here stat being manifested by question 12. Peer being manifested by question 3. These are all, kind of theoretical constructs. Does this theoretically make sense? We would have to talk about. We could also look at the covariation between question 6 and question 7. We can also just look at our model again. Do we have decent factor loadings? Some of the things we'd want to look for here is the factor loadings for some of these variables. It looks like question 10 here has, loads weekly on the computer fear items. Maybe we want to go back and look at question 10. Computers only useful for playing games. Is that how much does that relate with? So let's look at questions 6 and 7. I have little experience from computers. Computers hate me. We want to think about, does that really make theoretical sense to go with these other items? Does the scale still make sense without it? These are just different questions that we want to ask ourselves. Question 20 on stat fear, is low, but not too bad. Everything in the math fear loads pretty highly. Look at question 23 here. It's got a pretty low factor loading, right? 0.256. You'll see lots of citations that I think the lowest I've seen is like 0.32. You typically want your items to load onto your factor at least 0.32. I think that's the recommendation like Tobocznik and Fidel give in their multivariate book. I've even seen some you want like 0.4 as the minimum. So, that's something that we would want to look at. Question 23 is the peer evaluation. If I'm no good at statistics, people will think I'm a nerd. It seems to relate to the other ones, but maybe it's just not as strong as the other items. Another thing that sticks out to me, look here, we can get the correlation between question 20 and 21. See, it was 0.231. Another thing that really sticks out to me is the correlation between computer fear and statistics fear is 0.839. It's saying that those latent constructs are highly correlated. That maybe we have too many latent constructs here. Maybe it's really just one. Maybe it's stat and computer fear are really the same thing. It's all statistics kind of anxiety, statistics / computer anxiety. Maybe they're measuring the same sort of concept. There's also a pretty high correlation with the math fear items as well. Here's some just different interesting things to talk about. Here's where I talk about some of the modification indices. We talked about that. We kind of talked about here about the danger of only relying on the modification indices. You can really just overfit your model to this particular sample of data rather than what's actually happening in the real world. So the next thing I suggested was, if you go through the example, is question 23 here doesn't have a high factor loading. The latent construct isn't explaining a lot of the variance in that indicator, that maybe we should just get rid of it. So I ran a new model here where I just dropped question 23. See, it's no longer in the peer evaluation item set. We can fit our model and get our summary of the results here again. And you can see our chi-square decreased again, still statistically significant. The CFI and TLI increased some. The root mean square of approximation is about the same. The SRMR went down some. These models aren't nested because there's different variables in each model. So a likelihood ratio test wouldn't be appropriate, but we can use kind of that same syntax we had before and just get the fit measures from model 3 and model 2, the root mean square of approximation, the TLI, the CFI, SE, BSE, and just put them together in a table here so we can kind of see what's going on. So you can see there's no question 23, and this is with question 23. Notice the TLI, the CFI improved, the ASE and BSE all decreased, which indicates slightly better model fit, but the root mean square of approximation slightly increased. So, it improved the model fit marginally. You can keep looking through here. Question 10 also didn't fit very well. We could practice going through here and removing it. If the statistics end up being a little bit better with it too, but I'll leave that for you as kind of an exercise to play along. See if you can find a really good model fit with these data that is also theoretically sound, that we could theoretically justify too. And you can think back too about the EFA. Should we have really included all of these items in the CFA to begin with? Peer evaluation had a really bad reliability. Was that even appropriate to include in here? Those really are defined by just one factor. Is it really just anxiety that's defining all of these constructs? So I'll leave that to you as like a fun exercise you can do to play around with these data. Another thing we can do besides just looking at the item fit and the item fit, the model fit, and modification indices is we can inspect the correlation. So just basically, so this kind of do like a residual analysis, similar to what we did in the EFA. The whole idea here is that if the model implied covariance matrix or correlation matrix does a good job of reproducing the observed correlation matrix, then the residual matrix would just be the difference between the model implied and the observed. There wouldn't be any correlations left, right? That the latent constructs did a good job of explaining the variation in our item set, then there wouldn't be really any large residual correlations left. So here's some syntax here. If we wanted to look at, so here's, if we wanted to see, here's what the model implied correlation matrix would be, from our model. It's implying that there are these relationships among the variables. Here's the observed correlation matrix. And then you can get the residual correlation matrix. And basically, you would really call the residual correlation, you're looking for high residuals. Different people define them different ways. I think in that Klein article, he talks about residual correlations greater than 0.1 indicate a lack of fit between the model and the data. Klein even recommends reporting this residual correlation matrix in a write-up of your CFA to give your reader the residual correlation as another indication of how well the data fit. Even will also give you like standardized residuals. And so you can look for standardized residuals greater than 0.3. Here, this is some similar code to what we had in the EFA, where we took the residual correlation matrix, and then we sorted it to only look at like the upper half of it, and then we looked for correlations greater than 0.1, and then I sum those and then get the average of them. So it's just a block of code that does that. So we can see there are 22 residual correlations that are greater than 0.1, and that represents about 9% of the data. And so, Klein says that, residual correlations greater than 1, kind of indicating this bit, is 9% of them a big deal? That's kind of something that you'd have to decide, and you would have to say, you make the argument in your right about whether or not you think that then represents a good fit. Whoops, wrong way. And this I was doing based on our second model, so fit 2, so it was where the question 20 and 21 were correlated. Here's the same thing, but we're using the standardized residuals, and we're looking for standardized residuals greater than 3. And the rest of it is just a few little extra tidbits. Here's some sample size rules of thumb. Typically, we want around 10 to 20 observations per estimated parameter. And so how many estimated parameters are there? So here's a formula to kind of figure it out. You can get, the number of indicator variables plus the number of covariances times 2 plus the number of covariances among latent factors. I think this is one of the formula from one of the readings. I don't remember off the top of my head which one. So in our example, we have 23 indicators and 6 covariances among our factors. Remember, it was statistics sphere, computer sphere, statistics sphere, math sphere, statistics sphere, peer evaluation, comp, math, and then in comp sphere, right? Well, we can go up here and I'm going. That's not the. Where did I stop? I meant to change this. I was trying to get that back. So right, so comp stat, comp math, comp peer, stat math, stat peer, math peer, right? So that's 6. And then the number of indicators. So that's where this came from. Remember here, I think this one we didn't have question 20, so we had less number of indicators. That's why it's 51 instead of 52. If we go back to our first model, way up here at the top, so 52, same that we found here. So, according to this rule of thumb, we'd want to have a minimum sample size of around 520 to around a little over 1,000. So we met kind of the minimal sample size requirements according to that. We already talked about this, comparing models with the likelihood ratio test. Some things people would usually compare is, if you want, say, like an orthogonal model, so you don't want a correlation between the factors. It'd be essentially, like an orthogonal rotation in CFA. You can just use, if you want to turn off that covariation between factors, you can just use this command orthogonal equals true. And you can, so here we go. So notice here, there's no covariation between the factors. We still have the covariance between question 20 and 21 because we explicitly asked for it. We could also compare our model 2 with one that's just for SPSS anxiety, I call it. So basically a one-factor model. And you can see, it looks like here that, the multiple factor model fits the data better than the one-factor model. LAFIT also has some really nice features for robust estimation and a really nice feature for missing data. So you can get robust maximum likelihood estimations, which is basically going to give you those Huber-White standard errors that adjust for some types of model misspecification. So like if our data really aren't normally distributed, we might want to use like the robust maximum likelihood estimator. And it's really easy to do. Just add this, add the estimator to your CFA command, add estimator equals MLR, maximum likelihood, the robust maximum likelihood. It also handles missing data using a full information maximum likelihood estimator. Pretty much under the assumption that the data are missing at random. All right, if the data are missing not at random, the full information maximum likelihood appropriate tool for missing data. But it's a lot full information maximum likelihood is a lot easier than especially to interpret. It's not as like, I don't know about computation, but it's a lot easier to interpret than like a multiple imputation. So it's another method besides using like a multiple imputation for your data set. We skipped over this at the beginning, mainly because the data aren't normally distributed. But when you use maximum likelihood estimation, one of the assumptions is that your data are multivariately normally distributed. So you might want to check for that. Back at the beginning when we were examining our data set. So there's a function in the psych package we can use to check for multivariate normality. So there's a Martina test of multivariate skewness and kurtosis, and then we get a little QQ plot here. If our data were multivariate normal, these dots would follow along this 45-degree angle. We notice at the tails of the distribution, it's not, indicating that if the data aren't multivariate normal. Same thing with the multivariate skewness and kurtosis test. They're both statistically significant, indicating that they're not normal. The MVN package also has a test for multivariate normality, and it does. So this is going to print histograms for each one of our variables, and it's going to give us a multivariate normality test and individual univariate normality test. You can see here's the same multivariate skewness and kurtosis coefficients, and notice it says no, not multivariate normal. And here are univariate normality tests for each one of our variables, and I like it says no. So it tells you straight up what's going on. You can see here it also prints out some more descriptive statistics. Here are the histograms, so you can see. I mean, we knew these were categorical data. So with only, was it 5 response options? What, I forgot. Yeah, 1, 2, 3, 4, 5 response options. So, it might be questionable whether or not we want to treat these as continuous data. If nothing else, I would probably use the robust maximum likelihood estimator. Another option is to use the weighted least squares estimator, and Laban also has a special function that works with categorical data. So, you know, for nominal categorical data, you have to do just like you do in traditional regression analysis and create dummy variables for nominal categorical variables. For ordinal variables, it has an ordered option where it will then basically analyzes like the polychloric correlation matrix and estimates thresholds for each one of the categories. Because you know the idea is that these ordered categorical variables are sort of being manifested by, you know, an unobserved continuous variable that we can't directly measure. We can measure it using these ordinal variables. So it kind of takes that idea, same idea from the polychloric correlations, and estimates it. And you can read more about it, so it takes a little bit more time to estimate. But basically, we get sort of the same results. If you're doing this, use the, you know, we would use kind of the robust estimates over here on the side, and you can still interpret them in a similar fashion as we did, you know, as we did before. Here are factor loadings for our variables. You know, this is one with question 23. Remember, it didn't. You know, we still get correlations between the factors. And then there are the threshold parameters, which you can pretty much ignore. Our variance estimates, and then same R-squared values. You can read up a little bit more about it. Here's kind of a technical paper about it, but that's where I get where they recommend using the robust estimates of model fits if you need a citation for it. Here's some information if you want to like kind of inspect your models. You can kind of read through here and see more if you want, you know, information about different options in Laban. You know, you can run this command. We've already looked at the reliability and giving you the average the average variance explained. And here's just some syntax using the SEM paths command in the SimsPlot package. It's a lot more flexible than the Laban plot package, but the syntax, notice, isn't as clean to use, but it's another way of getting a graphical depiction of your data. So that was our quick walkthrough. I don't know how quick it actually was, but that was our walkthrough of confirmatory factor analysis. We'll go through an exercise again in class about this. But, you know, if you have any questions, you know, shoot me an email, stop by my office, post to the message board. I'm here to help. Hopefully it's annotated very well for you, so if you're walking along, you can kind of read and follow along with it too. All right, if you need anything else, just let me know. Thanks. Bye.